Welcome to my channel. This is a presenter from the channel. Ocean sediments are usually not at the top of people's minds when they think about dinosaurs, but it turns out that these geologic deposits may have played a key role in the mass extinction that wiped out the dinosaurs 66 million years ago. And by studying ancient mud, scientists may have just found evidence for what really killed off the dinosaurs. Now, ocean sediments themselves are pretty simple. They're made up of particles of rock, minerals, and organic matter that settle out of the water column over time. As new layers build on top of older ones, they form sedimentary rocks like shale and mudstone. The composition of those rocks can vary depending on where they're located and what's happening in the environment at the time they're forming. And because they preserve well in the fossil record, they can tell us a lot about the history of the Earth. And recently, researchers turned to ocean sediments in South Texas to try and solve one of the biggest mysteries in all of paleontology, what actually caused the extinction of the dinosaurs. For millions of years before their eventual demise, dinosaurs dominated both the land and the sea. But then came the asteroid impact that formed the Chicxulub crater and wiped out not only the dinosaurs, but 75% of all species on Earth. But while the asteroid is to blame for the mass extinction, the details of how and why it did so are still up for debate. It's generally thought that the impact triggered a chain reaction of devastating events, including massive earthquakes, tsunamis, wildfires, and volcanic eruptions. Then there are the more familiar effects like climate change and an ice age. But no one knows for sure what combination of events played out after the impact or how each of them affected the biosphere. And it's hard to pin down the relative importance of each of these secondary effects because most of them happened at the same time and left their own distinct signals in the geological and fossil record. So it's like trying to parse out the individual notes in a very cacophonous, chaotic, disastrous chord. The good news is that ocean sediments may help us tune out the background noise. That's because these deposits often preserve tiny fossils called microfossils. Microfossils are the remains of microscopic organisms like plankton that swim in the water column. As they live their lives, they accumulate in the water and eventually fall to the seafloor where they're incorporated into the sediment. So analyzing these fossils can tell us what was happening in the oceans at different times in the past. And if we're lucky, we might even find microfossils from right around the time of the asteroid impact. In this case, though, luck was definitely not the word. A previous study led by University of Texas at Austin Jackson School of Geosciences professor and marine geologist Joanna Mountain had already collected sediment samples from ODP Site 1249 in the northern Gulf of Mexico. She and her colleagues knew that this site contained sediments from just before and after the extinction event. They just didn't know how fast the sediments built up on the seafloor. To figure that out, they needed to conduct what's known as a smear slide analysis. To do that, the team carefully scrapes a small amount of sediment off the core and mixes it with water. Then they drop a few grains of the sediment onto a glass slide to make a smear. Under the microscope, it looks like toothpaste. Then the team counts the number of different types of microfossils to get an idea of what was going on in the water column at the time these sediments were deposited. In this particular sample, they found Foraminifera, which are single-celled organisms with shells made of calcium carbonate. There were also radiolaria, which are made of silica, and are a bit more delicate, so their shells rarely fossilize. This meant that the researchers could use the Foraminifera to figure out how quickly the sediments accumulated before and after the extinction event. That's because the radiolarians should have been completely wiped out, but they weren't, indicating that there was some sort of interruption in the deposition of new sediments. Once they knew how fast the sediments were accumulating, the team could estimate how long it would take for oxygen levels on the sea floor to return to normal after the impact. Oxygen levels, you ask? Well, there's another line of evidence that suggests something interesting about how the asteroid impact affected the oceans. A few years ago, geochemists started to notice strange chemical shifts in deep seafloor sediments from the late Cretaceous. Basically, they saw a bunch of elements that don't usually hang out together, all that often hanging out together in a pretty uncharacteristic way. And that weird chemical fingerprint appeared in other places too, suggesting that it was a global phenomenon. Now, this pattern appears right at the KPG band, which is a thin layer of sediment that marks the end of the Cretaceous period and the beginning of the Paleogene. It's defined by a spike in the element iridium, which comes from the asteroid. But these strange chemical patterns go beyond the KPG boundary. So these chemical shifts probably weren't caused by the impact itself, but rather by the consequences of the impact. The team responsible for that original study suggested that the changes might have been caused by the release of hydrogen sulfide from the seafloor. Hydrogen sulfide is toxic, even in low concentrations, and is usually kept in check by oxygen. But if oxygen levels dropped, that would allow the sulfide to escape and poison the water column. However, other scientists pointed out that the chemical signature did not look exactly like hydrogen sulfide, and the timing was a little off. If this was the cause, we should have seen similar chemical shifts in shallower waters too, and we haven't. So the jury's still out on whether or not this mysterious shift was caused by hydrogen sulfide or something else. But no matter what it was clearly a response to the asteroid impact. And now the team has shown that a drop in oxygen levels could explain the full suite of chemical changes. In other words, it wasn't hydrogen sulfide specifically, but instead, any process that reduces oxygen levels in the ocean could be responsible. Because many of these secondary effects likely overlapped both in time and space, figuring out which one is having which effect can be difficult. But the team thinks that low oxygen levels may have been the ultimate cause of the disruption. You see, the asteroid impact likely sparked massive earthquakes and triggered huge waves. These giant tsunami waves could have churned up the bottom of the ocean and displaced huge amounts of water. All that mixing could have brought up molecules called sulfides, which are bound up in the seafloor, and released them into the water column. Other chemical changes in the water could have followed suit. Iron and manganese would have become more available, and nutrients like nitrogen and phosphorus would have become less available. Eventually, though, things would have returned to normal. That is, unless the asteroid impact caused other changes like volcanic activity or climate change, which could have prolonged the disruption. The team thinks that these changes in nutrient availability could have disrupted global ocean circulation patterns and contributed to the extinction of plankton. This plankton extinction could have caused major problems for the animals that depended on them, like the dinosaurs. And since the team hadn't been able to answer the question of how long it took for oxygen levels to return to normal, they couldn't say whether or not the low oxygen levels persisted long enough to cause such an extinction. Smear slide analysis to the rescue. By counting the microfossils in the sediments, the team determined that the entire disruption lasted only about 2 to 3 months. That duration would have certainly been long enough to cause a plankton extinction and subsequently cause the extinction of the dinosaurs. Not only that, but the fact that the chemical changes happened so quickly tells us that whatever caused them was probably a global phenomenon. Together, these lines of evidence paint a pretty grim picture of what life was like in the oceans immediately after the asteroid impact. But the story doesn't end there. Just because the team has identified a plausible mechanism for the mass extinction does not mean that we've solved the mystery of what killed the dinosaurs. Ultimately, it'll take more evidence to say for sure. But this study does show that ocean sediments can tell us more about what happened to the dinosaurs than the dinosaurs themselves. And you know what else I love about this story? We got to talk about two of my favorite things, dinosaurs and poop. Check out this video to learn about dinosaur poop and why it's making scientists so happy.